Hey there students, Mr. Fuger here. In our video today we're going to take some time to look at our next lab dealing with our smart cards, Lab 1E, what we call Time to Get Smart. Now depending on the year in which you're watching this video, the numbering may change just a little bit, but this should remain the same title of our lab, Time to Get Smart. So what we're going to do here in our video is talk a little bit through the setup of what we're doing in the lab, and then I'll actually walk through kind of a sample of how to collect data and do a bit of analysis. For those of you that might be working remotely, you can actually use the data that I collect here to be able to complete things on your own. So I would suggest if you are working on completing things remotely, that you do go ahead and make sure you have access to the lab sheet. That way you can make sure to reference the main information. I'm not necessarily going to be reading through the entirety of the sheet, but I will hit the main points and highlights as we go. Okay, so effectively what we're going to be doing here is checking a hypothesis made by a student that deals with the velocity of the cart, how fast it's moving as it moves down the track. So our student's hypothesis goes like this. The velocity of the cart will increase as the cart moves down the track. The best method to predict the velocity at various points is to use a kinematic equation. If we can determine the initial velocity of the cart at one point in time, we can then use the displacement of the cart and time to figure out the final velocity at another point. So what this student's saying effectively is this. If I were to take the cart and let it go down the track, if I were to choose two different points, let's say if I let it go, if I were to choose a point here and then maybe another point here, what we could do is we could collect some data on where the cart's located at each point and how long it takes to get from one point to another, and we could use that information with a kinematic equation to make a prediction on velocity. Basically, the student's saying here, the kinematic equations work as long as, when we're dealing with these real life scenarios. They're not just things we can use in fictional situations, they're real equations that work for real life values. So what we're going to do is we're going to walk through a couple of trials, one where I have the ramp propped up with one book and one with two books. We're going to collect some data and then use specifically the fourth kinematic equation to check and see, does the velocity we predict actually match up with what the students are saying? So hopefully that gives us a decent overview as to what we're doing. Now what I'm going to do is come into the procedure section, and I have a few screenshots in here so that if you're working on things remotely, you can see roughly what we're looking to do. Now what I'm going to do here in a moment is I'm actually going to release the cart from rest. I'm going to pick some points along its motion down the track. I'm going to use those points to use my kinematic equation and then predict what's going on with the velocity. Basically what I have here in the screenshot is an example of what you would be doing if you were working through things on your own. You'll notice here I've got an initial point and then a final point. And what I can do there is I can use the information from those 2 points in my kinematic equation to predict what's going on. Now, what I'll do is I'm actually going to scroll down here so I have the space to be able to fill in with my data. Now, as I do this, hopefully I'm going to put a little screenshot in here or a kind of a picture-in-picture that will show the data that I'm collecting and then where I'm getting my numbers from. Okay, so I'm going to get my cart up here on the high end of the track. I'm going to take a moment to make sure I zero out my position sensor and then I'll release from rest. Okay, here we go. 3, 2, 1. Go. Okay, I'll go ahead and stop there, bring my cart back, and I'll add in my second book. I'm going to go ahead and get both of my trials of data first, and then I'll pull my numbers. Okay, position is pretty much zeroed. Okay, 3, 2, 1, go. Okay, bring the cart to a rest. Okay, so now I have my 2 trials of data. I'm really quickly here just going to rename them. So I've got data set 1 was here just with one book. So I've got to rename data set. I'll do 1 book. And I'll go to my second data set. I'll hit rename. And data set 2, I'll do 2 books. Okay, so I'm going to start with 1 book. I'm going to go ahead and turn my data table off. I'm going to come back to position for 1 book and velocity for 1 book. I need to turn velocity for 2 books off. Okay, now really it's up to us what points we choose. We just want to choose 2 points in which the cart is actually moving. So like I showed you in the screenshots, I'm just going to choose some initial point and some final point. Hopefully points that are a little bit further spaced apart so they're not right next to each other. Okay, so I'm going to go with, let's say, this point here. Okay, so my initial position for my one book trial is 0.108. 0.108 meters. The velocity at that point, if I'm reading it off of Vernier, is 0.256 meters per second. And the time was 1.5 seconds. Now, that time, just so we're clear, that's the time it took from when I hit collect for the cart to get to that point. I usually, when I'm collecting data with the carts, will give a little bit of a delay, just so I can make sure the data is getting sent over to the Chromebook. Okay, I'm going to scroll to another point. As long as it's prior to the cart hitting the wall, we're good. So we'll go about here. And my next time is, I'll actually come back. So my next position is 0.734 meters. Okay, and then my final velocity here, or my velocity at this point, is 0.662 meters per second. I'm going to put a star by that number because that's actually a number that we're going to try and predict from the equation, and then we'll come back to it. So I'm not going to put that number into my equation, but I will come back to it later. And then my time here is 2.86 seconds. Okay, so these would be all of my data points from my first book trial. Now I'm going to go through and do the same thing for my second book. So I'll turn my position on for book 2, off for 1, velocity on for book 2, and off for 1. Okay, so for 2 books, I'm going to go with, I'll just call this my initial point about right here. Okay, so initially, for my 2 book trial, I'm just going to choose a point of 0. Try to do this in a different color, so I have a little bit of a distinction here. 0.105 meters. My velocity at this point is 0.359 meters per second, and the time was 0.94. A little bit less of a delay here. Okay, and then my final point, I'll just choose another one. Slide this down. As long as I haven't hit the wall yet, we're good to go. Because again, we're just looking at the cart's motion going down the track. Once it hits the wall, there are some other forces that get introduced, and we're going to stop looking at its motion there. We're just looking at, during this one case of motion, when we have just an acceleration from gravity, what's going on. Okay, my position here is 0.696 meters. And then my velocity at this point is 0.922. Scroll down just a little bit. 0.922 meters per second. And then my time at this point, 1.86 seconds. Now you'll notice with the second book trial, it's going to take less time for the cart to get to the bottom of the track because we have a steeper incline. And so that should be what we expect to see. So what I'm going to do now is I'm going to go through it with the data for one book. I'm going to use that data with my kinematic equation to predict what's happening here, and then check that with my final velocity. I'm going to leave the second book trial up to you, but hopefully you can use the first book trial as a bit of a template on where we're going to go. Okay, so for one book, I'm going to go ahead and fill in that the actual final velocity here was 0.662. All right, I'm going to double check that real quick. I want to make sure it's not 622, so my time is 2.86. Okay, we're good. Okay, so I'm going to come over here. Okay, so my actual final velocity for one book is 0.662 meters per second. And we're going to try and use an equation to calculate what the final velocity should be, and then we'll compare things. So, how are we going to do that? A few extra things in here. Okay, so our delta x, we're going to find our delta x by looking at the difference in where the cart was positioned at each time. So if I come back, My initial position was 0.108. My final position was 0.734. So my delta x is going to be 0.734 meters minus 0.108 meters. And that should give us about 0.626. Let's check 734 minus 0.108. 0.626 meters. Okay, we'll come over here and fill that in. So my delta x, 0.626 meters. Okay, final velocity is what we're looking for here. Don't know that, we're looking for that. We do know the actual final velocity, but we want to see if the equation matches up. Our initial velocity here, I can just fill this in directly from my initial data points. Initial velocity was 0.256. 0.256 meters per second. The acceleration down the ramp, we don't know. And then our time is going to be the difference in our time at our initial point and our final point. So if I come back here, my final time was 2.86 seconds. So time is equal to the difference in our final time minus our initial. We can kind of think of this as the difference in time between our 2 points. So I'll take 2.86 seconds minus 1.50 seconds, and that should give me 1.36 seconds. So there's the time that passes from our initial point to our final point. Okay, so bring that back. 1.36 seconds. Okay, so I did give us a bit of a hint as to what equation we're using, but in case we didn't catch that or see why, we're going to choose the equation that doesn't have acceleration, because that's the variable that we don't know, and also that we're not really concerned with. So I'm going to write out equation number 4. Delta x is equal to 1/2 multiplied by v1 plus v0 all times t. Okay, so let's plug in what we know. Our delta x, 0.626 meters, is equal to 1/2 multiplied by v1 plus v0, which is 0.256 meters per second, multiplied by our time, 1.36 seconds. A little cram there, sorry about that. Okay, now there's a couple things that we could do here in order to solve this, but one thing I want to draw your attention to. This term, v1 plus v0, because it's in parentheses, I cannot mathematically just subtract out my velocity term, because this is in a set of parentheses, meaning I have to treat that as if it's one term. I could go through and maybe distribute the 1/2 or the 1.36, but I'm not going to do that because I think there's an easier way. So here's what we can do. I'm going to take the 1/2 and I'm going to multiply that by 1.36. I'm going to leave the term in the middle by itself, and I'll show you why here in just a moment. So on the left-hand side, we still have 0.626 meters is equal to 1/2 times 1.36. Let's find that. That's going to give me 0.68. My unit there would be seconds. And I still have this term in parentheses, v1 plus v0, 0.256. Now again, I could go through and distribute that 0.68 term, but I'm not going to, because my goal is to try and get everything away from v1. I want v1 to be by itself here. So I'm going to divide both sides of the equation by 0.68. 0.68. So any number divided by itself is 1. So that term will cancel on the right, and I'll take 0.626 over 0.68. And I get about 0.9205. So I'll call this 0. As the board gets a little frozen up. Oh. 0. Interesting. Trying to get this in blue. Okay. 0.921. That would be meters over seconds. So meters per second is equal to my final velocity plus my initial 0.256 meters per second. And then lastly, to get my v1 term by itself, all I need to do here is add over, I'm running out of space here, or sorry, subtract over 0.25, man, my fives are having a little bit of a hard time. 0.256. That is in meters per second, so those are like terms. I can add and subtract them. So any number subtracted by itself is 0. I'll take 0.921 minus 0.256, and I'll get 0.665. So the final velocity I should be getting, according to my kinematic equation, is 0.665. That's what my final velocity should be, according to my equation. So when I come back to my data table here, the calculated final velocity is 0.665 meters per second. And now we have a number to compare to our actual final velocity. And just kind of at a quick glance, those numbers look really, really close to each other. Now, one thing that we can also do is we can also calculate what we call percent error. How much error is there between the number I calculate and the number I actually saw? Well, I can actually follow this formula. I take the actual value minus what I predicted, and then I'll take the absolute value of that difference. All that's really going to do is take our number and treat it as a positive, even if it's a negative. The numerator in our percent error equation is all about how far away our actual value is from the predicted value. Okay? And then we divide by the actual and see, as a percentage, how far away our numbers are. So for one book, my percent error would be, call that percent E. I've got the actual, 0.662, minus my predicted, 0.665. I'm going to leave my units off for now. Divide by the actual, 0.662, and then multiply by 100. Okay, so 0.662 minus 0.665, absolute value, so that will take that number and make it a positive. Divided by 0.662, multiplied by 100, and I get 0.453%. Which is telling me that my my calculated value is less than half of 1% away from the actual value. Now, why are we doing this? Well, remember the hypothesis that we're trying to check. The student is predicting that the actual final velocity can be found by calculating for it with a kinematic equation. Our whole goal in doing this is to try and see, do the equations work when we're using real numbers that we're collecting? A lot of times in the problems that we're looking at, we're just given numbers that describe something. But here, we're actually seeing when we collect real numbers with real equipment right in front of us, and we use our kinematic equations, we're showing those equations are pretty spot on. Now, you may be asking, why is it not exactly 0.662? Why is our calculated value not the same as our actual value? Well, remember, our equipment here is only accurate to within a certain degree. If we're getting something that's within even maybe 3 to 5%, maybe even a little above that, that's pretty good confirmation that our equations are working. We shouldn't expect to see 0% error because it's almost impossible to get data down to that level of precision. If we're within something like what we're seeing here, or even again up to about 3 to 5%, that's pretty good confirmation that our equations are working. If we were seeing something that was 10, 15% error or above, that's probably a reason for us to not support the student's hypothesis. So this overall should give us pretty good confirmation that the student's hypothesis is in fact correct. Our kinematic equations work, and they can allow us to predict things like velocity or other things depending on what we're trying to do. And that's one of our big takeaways, is that I want you all to see the equations really do work, even when we're using real numbers in the real world. So hopefully this gets you going in the right direction with working on Lab 1E, how to collect the data, and how to analyze that data. If you are working remotely, you're welcome to use the numbers that I collected here. I've kind of walked through the analysis for the first book, but I'll leave the analysis for the second book to you if you're working remotely. As always, if you have questions, please feel free to reach out to your instructor and let us know. Other than that, good luck.